In this video, we're going to apply our quantum proof 2 universal hashing based extractor to a simple example. Let's see how it works. So here is a possible family of states that could represent side information about our input. So the input here is an element of 1, 2, 3, 4, 5. And the states that I've written up there, they correspond to the side information. So we want to design an extractor to apply to this input. Here there's 5 possible inputs, so it's natural to think of them as elements of the finite field F5. In this case, we need to design a family of 2 universal hash functions from F5 to the output of the extractor. And we saw an example of such a family. We can take the set of all FAB, which map X to AX plus B, where A and B are elements of F5. So this is going to be our family of hash functions. And then the extractor will take as input an X and the label of a hash function, so a pair A and B, this is our seed Y, and we'll map it to FAB of X, except that we actually want to hash these down, so we want the output length to be smaller than the input length. Remember, the condition for the 2 universal hashing extractor to work is that the output length m satisfies that it should be less than the input min entropy k divided by 2 minus log 1 by epsilon, where epsilon is the target error that we want to achieve. So here, because the input takes only 5 possible values, it kind of doesn't really make sense to set an epsilon and k. We'd have to compute the min entropy of the source here. So let's just save and hash this down to just 1 bit. So what we'll take is we'll take this output and take it mod 2. Look only at the parity. So that's my extractor. Let's compute it and see what it gives on an example. So let's take an example choice of a seed that's random. Let's take A and B to be equal to 2 and 3. And let's do the computation. Let me write a little table. Let's have the different values of x. So let's say x is 1. Then what is FAB of x? I have to take twice x plus 3, so this gives me 5. 5 in F5 is just 0. And the output of the extractor will be this mod 2, so which is again just 0. Okay, so we do the same thing for x equals 2. Twice 2 is 4, plus 3, that's 7. Mod 5, I get 2, and the parity is 0. So we can do this for the remaining inputs, and here's the table that we get. So what is the side information now, depending on the output? So I have 2 states for the output. So I have either z equals 0, and y here is going to be 2, 3. So if z is 0, then it means the input x was 1, 2, or 3. So I have to add up the 3 corresponding states. So I'll get a fifth of 0, 0, plus a fifth of 1, 1, plus a tenth of the identity. And I get 1/5 of the identity plus 1/10 of the identity, so that's 3/10 identity. And if I look at z equals 1, the same seed, then what I get is that a fifth times fifth plus a fifth minus, so we get 2/10 identity. So what happened here? Note that this side information is not completely independent of the input 0. In one case, I get the identity scaled by 3/10. In the other, the identity is scaled by 2/10. The reason for this is that my example is too small. Also, I'm taking things in F5 and then mod 2, and when I mod 2, there's 3 elements that have even parity and 2 that have odd parity, so this is not balanced. So this is an artifact of this simple example. What's more important is that you see that in both cases, the matrix became the identity matrix. So there is some mixing that has happened by applying this extractor, and you can check different seeds and you'll see a different kind of mixing. So if my example was not such a finite size, what you'd have been able to see is that the output looks pretty much uniform, even though the input was not uniform at all, right? So I haven't computed the min entropy for you. You can do it as an exercise, but you'll see that, of course, this has significant side information about the input x, right? So my source is far from having full min entropy. So anyways, this gives you a way to compute the extractor on a small example. Hopefully it gives you a sense on how this object works in practice. And this concludes work for this week. Next week, we'll turn to quantum key distribution.